Hi, I'm Roland Minton. These are some of my favorite math stories. In this episode, Mathematics is the Mandelbrot set. This is part 2 of an exploration of the Mandelbrot set, one of the most remarkable objects in mathematics. I assume that you've watched part 1. As a reminder, here's the definition of the Mandelbrot set. For any point P equals AB, form the complex number C equals A plus BI, and iterate the function f of x equals x squared plus c starting at 0. If the iterates blow up, P is not in the Mandelbrot set, and P is colored based on how fast they blow up. If the iterates do not blow up, P is in the Mandelbrot set, and you get spectacular images from this definition. In this episode, we take a closer look at how the iterates behave within the Mandelbrot set. Here are some examples of iterates of functions of the form x squared plus c for some simple values of c. If c equals 0, we iterate x squared, starting at 0. 0 squared is 0, 0 squared is 0, repeating one number forever. If c equals negative 1, we iterate x squared minus 1, starting at 0. 0 squared minus 1 is negative 1. Negative 1 squared minus 1 is 1 minus 1, which is 0. And we bounce back and forth between the two numbers 0 and negative 1. They're harder to find, but other values of c cause a cycle of 3 numbers, or 4 numbers, and so on. Amazingly, these values are highly organized in the Mandelbrot set. For all c values within the cardioid region labeled 1, the iterates converge to one number. We saw that c equals 0 works this way. For all c values within the circle 2, the iterates converge to two numbers alternating. We saw c equals negative 1 work this way. For all c values within the region 3, the iterates converge to 3 numbers cycling around, and so on. Isn't that remarkable? Well, there's more. Let's find some patterns in the numbers. Start at the 1 and move to the left. There's a 2, and then 4. What's next? Well, they get smaller and smaller, but to the left of 4 are bulbs labeled 8, 16, 32, and so on, the powers of 2. As you move radially from the center, the cycle values double. Up above the 3, you'll find a 6, 12, 24, and so on. Now, start at that 3 at the top and go clockwise. The largest bulb to the right is labeled 4. For all c values in this region, iterates converge to a rotation among 4 numbers. Continuing clockwise, the largest bulb is labeled 5, a little hard to see in this graphic. Can you guess what's next? Yep, 6, 7, 8, and so on. Positive integers continue all the way down to the cusp, which actually occurs at the point 1/4, 0. Now, go back to the 3 at the top and look counterclockwise. The largest bulb between the 2 and the 3 is a 5. The largest bulb between the 5 and the 3 is an 8. The largest bulb between the 5 and the 2 is a 7. Yeah, the numbers add up. If you're familiar with the Fibonacci sequence, you can now find it on the Mandelbrot set. 2, 3, 5, 8 is a great start. But wait, with apologies for sounding like an infomercial, there's more. Here are magnifications of the 3 bulb and the 5 bulb up at the top. Count the green threads coming out of the end of each bulb. The 3 bulb has 3 of them, and the 5 bulb has 5. Counting clockwise from the main branch, notice that the longest thread on the 3 bulb is the first one you encounter. Notice also that mini Mandelbrot making an appearance. So call this the 1/3 bulb. Off of the 5 bulb, the longest thread is number 2. So this is the 2/5 bulb. Now, we already know that the largest bulb between the 3 and the 5 is the 8. Any guess as to how many threads this has? It has 8. Which one is the longest? Well, the longest we had 1 and 2 from 1/3 and 2/5. We added the 3 and the 5 to get 8. So on the Mandelbrot set, 1/3 plus 2/5 equals 3/8. Fraction arithmetic the way you always wanted it, and you can see that here. The Mandelbrot set is full of amazing facts. I encourage you to explore more in books and online.